Okay, so as you can see on the screen, we have got this circuit that consists of a difference amplifier, or in other words, we call this as an operational amplifier. So it has got two pins as inputs, negative and the positive pins, and the final third pin is the output. The positive pin is grounded and negative pin receives an externally applied input signal by means of this resistor R1. Output is fed back to the negative pin of this amplifier through the combination, I would say a parallel combination of resistor R2 and a capacitor C. So here you have an external input, here you have an output of the circuit. We assume that the opamp or a differential amplifier has an open loop gain indicated by letter A, which is practically huge. Usually in practical op-amps it is 10 to the power 5 to 10 to the power 7. So how to quantitatively analyze this circuit, it is a question. So obviously we see that since the gain of the amplifier is assumed to be very high, we can apply the virtual short concept, which we have explained a lot earlier in our modules, which says since we assume the gain A is practically very high, ideally infinite, there is no voltage difference between the two pins of the operational amplifier. It means the voltage at the positive pin of the amplifier is same, or I would say the voltage at the negative pin of the amplifier is equal to the voltage at the positive pin of the amplifier. So positive pin of the amplifier is connected to the ground, therefore this ground potential comes here to the negative pin. We can indicate that like this. So that's the virtual short concept. This virtual short concept helps us to simplify the analysis. So we see that at the negative pin we have a 0 volt because of the virtual short now. So with that, what we can say, let's say you apply a signal at the input pin right here, and that signal has peak to peak or peak amplitude with a certain frequency f. If the frequency is very small than the pole frequency offered by the combination of R2 and C of this circuit, we can see that the impedance of the capacitor is huge, ideally infinity, because capacitance impedance is inversely proportional to the frequency. So if the frequency is very low of the applied input signal, capacitor acts as an open circuit because its impedance is practically very high. So in that case you only have resistor R1 and R2 into the circuit, and if I ask you what would be the output, that you have to think. So with capacitor acting open in this case, we see that we have this negative feedback of the op-amp, and the voltage at the negative pin is 0 volts. Alright, so what you can write, you can say there is this current here, let's say I1, okay, and then this current, there is this current also, let's say I2, and you can say that I1 is equal to I2. Incoming current is equal to outgoing current because of the Kirchhoff's current law. Okay, so I1 is basically UE minus 0 divided by R1, and I2 is 0 minus UA or VO divided by R2. So actually you see that this is an inverting amplifier, and because of that you can say the gain of the amplifier. Right here it's an open loop gain. Let me write here properly. This is an open loop gain, and your closed loop gain with the R1 and R2 in the circuit. Let's say VO. Right here it is VO, and this is VI. So VO over VI is minus R2 divided by R1. You can just solve and simplify the Kirchhoff's current law that I just wrote here. So you should get this expression, and this is your closed loop gain AC. Don't get confused with the A. A is open loop gain, AC is a closed loop gain. Okay, so you understood now what happens when the at the DC, when the frequency is very low than the pole frequency of this circuit offered by R2 and C. What if the frequency of the applied signal is very greater than the pole frequency FC offered by R2 and C combination? In that case, we see that the capacitor reactance is very low, making it practically short. We would say the capacitor now is acting as a short. That means this resistor is now short. So what you can see that this, because the resistor and the capacitor they are shorted, the output is directly connected to the negative pin of the amplifier. Let me just draw that properly. So you can see that the output is directly connected to the negative pin of the amplifier. And what is the output then? VO would be 0. Why? Because of the virtual short, this ground potential comes at the negative pin, and at the negative pin you have a 0 volt, therefore output is equal to 0 volt, right? So this circuit essentially is behaving something like this. If we draw the response of this circuit, it would be like this. The closed loop gain AC would start with the value of R2 over R1, taking a magnitude of it, and then at a pole frequency, at a very high frequency, output is 0, the gain is 0, and this corner where there is a distinction between pass band and the stop band of this low pass frequency response is the cutoff frequency offered by combination of C and R2. Okay, so hope you found this module useful. You understood how this circuit is working, how this amplifier with R1, R2 and C acting as a low pass filter, active low pass filter, right? If I ask you to apply Laplace transform and then derive the expression of the transfer function, we have covered that in lot of earlier videos. So with that, we hope you found this module useful, and till then you can stay tuned for more informative content like this, and wish you happy learning.